इसमें कुछ इंडेंटेशन भी नहीं है ठीक है और वो ब्रैकेट लोकेशन
Okay, we'll get started. I'm sure some people will come in a little bit late, but for now there's a lot to get through. So we'll get started. Yeah, like first thing is that if people join the class late, it takes a little bit of time for everything to process. So, hold tight and hopefully the administration will get everything synced.
The first homework you said is due 9th September, right?
Correct.
So can I do that homework if I'm not registered for the class technically?
Yeah, you can
To
go.
register for the class, I'm at the CU limits. I need to drop another class, and that's not fitting in my schedule yet. Basically,
Okay.
the class that I need to drop, I'm swapping it with someone else for a different timing that someone else needs.
Sure.
So I need that class as leverage to swap with them.
Mhm.
So that's why I can't drop it for this one yet.
Okay.
But
Yeah, I would say just do the homework, try to submit it by the 9th. I mean, I understand scheduling issues, if it doesn't work out, just email me. But otherwise, I mean, there's plenty of time, and it's a pretty short assignment.
thank you.
Whoa. Okay. Yep, just some reminders. So as was just mentioned, the first homework is due on Monday at September 9th at 11:59 p.m. As a reminder of the office hours schedules, the TA Cindy, her office hours are Wednesday, 6 to 7 p.m. Mine are right before class from 6 to 7 p.m. And they're held in the third floor bump space. I will say all of this is quite fluid at the moment because everyone's schedules haven't yet been determined. For now, we'll stick to 6 to 7. For now, we'll stick to in-person in the third floor bump space. But if we figure out that virtual office hours is better, then we might switch to that. I will say there's a very good chance that within a couple of weeks, my office hour times will change, but I'll let you guys know, the week when I change it. I'll let you know on Ed. Yep, homework 2 will be posted probably tomorrow. Probably tomorrow. It's a little bit of a longer homework, but you'll have 2 weeks to complete it. So all future homeworks are going to be 2 weeks. It's just homework 0 was 1 week. Make sure you have access to Ed. I just did the syncing with Canvas, so hopefully that's there. But if not, let me know and I'll add you. And then lastly, importantly, Gradescope. If you need the code, it's right there. Make sure you're in Gradescope so you can submit your homework in time. Just a note on accommodations. If you have any special accommodations, such as holidays throughout the semester that would prevent you from submitting the homework at a certain time, just let me know as soon as you can. Ideally as soon as possible, but understandable if not. Just shoot me an email and we'll try to accommodate around that. Okay, so I mentioned last class that there will be a final project as part of this course. And more details about the final project we'll talk about in a few weeks when we get closer to the announcement of it. For now, I just wanted to show some of the past final projects just so you can get an idea of what is possible as well as the freedom that you have. Hello.
Hello.
Hey. So I'm just talking about past final projects for the course because there's a final project for the course. So this final project was done by some people named Khan and Shriyash, and they created a language called CDSS, where basically, from my understanding, you write a bunch of constraints, and in this language CDSS, which gets compiled into CSS, and that gives you style or whatever. So this slide with the boxes and shadows was created using their language CDSS. It's pretty short. There's a lot of issues with CSS, especially when your views change in size. You have to specify a lot of different things. With their language, it worked a little bit better. Some other folks decided to create some asset portfolios, things like that. So just considered a bunch of stocks and tried to create a portfolio. It ended up performing quite well. So that's another thing that someone did. And here's another one, the generative melody creator. It basically created music or beats for pretty much anything using something called Euclidean rhythms. That's something else. All this is to say is that there's a lot of freedom into what you can do in the final project. So don't be too stressed about it. Just make sure you choose something that you're excited about and you can create something really, really cool. Like I said, more information about the final project I'll talk about, once we get to that time. Okay, we're gonna play a quick game for a few minutes. So I'm gonna give each one of you a sheet of paper. Ideally, you have a writing utensil. If not, oh well. You can work together if you want, and I'll explain how this game works. So, you all have a sheet of paper that looks something like this. And the way this works is I'll give you a very simplified version of the game. Let's say I have something that looks like this in this simple game. Your goal is to create a closed loop, so like a singular line that connects back to itself, such that when you look at a number, 2 of its sides must be a part of the loop. So like the solution to this would be this, that, and then maybe something like that. So that has 2, that has 3, and it's a closed loop. So you can work together. I'll give you a couple of minutes to try to come up with the solution. And as you're doing it, just keep note of like where you're starting, and inferences you're making along the way. And we'll see if people come up with the correct solution. So
if a square is empty, then there's no restriction.
no restriction. Yeah, I can have as many as you want. So feel free to work together and see if you can come up with the solution. Yeah. Yeah. So like, let me erase this. So you have like the grid of dots with numbers in here. You're going to like draw lines connecting the dots such that when you look at a number, out of the 4 things that create the box, only in this case 2 of them would have lines. So like if I start like this, that has 2, and then the solution that has 3, and it's a closed circuit. So yeah, I'll give you a couple of minutes since we don't have too much time. What's that?
It's just one circuit.
One circuit.
And the numbers all be inside the
Yeah.
circuit.
Yeah. Well, I mean, okay, they don't have to be inside of the circuit, but like
They just have that
the lines that create the circuit like have to be, outside.
That's another one.
Oh yeah, sure.
But I also get another one. I think I messed up
Another one?
the first time.
It counts.
I didn't print that many out, so let's say everyone gets 2. Because I don't have that many extra.
Can it be a conjunction of two closed loops?
No.
No, singular closed loop. Okay, I know I didn't give that much time, but did anyone solve it? No? Okay, that's all right. Let's back to the class. We'll worry about the puzzle later. You can solve it on your own time. But like, what were some of your first thoughts? Like, how did you approach it? Like, what did you do? You just started guessing, or
I started with the 0.
Yeah.
Okay, you started with the 0, and what did that tell you?
Well, at first I thought that meant there couldn't be any edges around it.
That's correct. Yeah.
That's not actually true.
Oh, it is true.
What?
Well, if it says 0, that means you cannot have any edges.
As long
Around
as
it.
the 0 is not contained in the shape, it's okay. Though, right? There could be an
No.
edge on
Like
right
the
hand
numbers
side.
can be outside of the shape, but like the line still must abide to that. Like if 2 is outside of the shape, I still need 2 of the lines to.
Okay.
Did anyone start with the 3s?
Yeah, I thought those corner threes were really cool because in order to make like the closed thing, like those threes like sort of have to like come be the edges of those like closed things. So like I kept my hand on the 0 and then started from those threes. Tried to go down.
Yeah, like one observation you can make is that in the 3 shape, like in this bottom corner, you can't like, there will be one open edge, and like it can't be this one or that one,
Yeah.
otherwise things would break apart. So like this is good. This is a very hard problem, which is why I gave it to you, because we're solving hard problems in practice. But this idea of like making observations about what you see and sort of like pruning how you go about solving things is what a lot of people do to solve very difficult problems. So I will show you the solution if you'd like. Otherwise, you can close your eyes. Okay, if you don't look at the solution, you have to promise to not work on it during class. Otherwise, I'll take away from your attendance points. Okay, so I'm going to flash the solution really quickly. Close your eyes. There. Okay, now you're free to not look. Okay, so cool. That was just a fun way to start things. So, questions?
Is there only one solution?
One that I know of. Maybe there's more. I don't know. Okay, cool. So last week was sort of the introduction to the class. We talked about what hard problems are, and then we introduced the SAT problem. If you weren't here last week, highly encouraged to read the lecture notes. The slides and the notes are posted. The notes are very long. They're like 8 or 9 pages, but I assure you they will be a lot more helpful than the lecture slides because they're a lot more verbose and they explain things a lot more. So I encourage you to read those. Today, we're going to look at SAT solvers, like tools that solve the SAT problem. And then we'll discuss some other problems and see how they can be encoded. So first, we'll just do a bit of review of the SAT problem. I'm just going to breeze through this. This is whatever we covered last time. So the SAT problem deals with these Boolean formulas. Usually we use the variable phi. So it's these variables that are either true or false. They're combined with logical operators. And we're asked the question, given this formula, can we assign values to these variables such that the entire formula evaluates to true? So the first example, we would say, yes, it is satisfiable because we can give these assignments and it would evaluate to true. The second one is unsatisfiable. We would say no. This is some of the terminology we used. First, we assumed that the only logical symbols are and, or not. We'll talk about that in just a moment. A literal refers to either the variable or its negation. A clause is this disjunction or of literals. So these parentheticals with literals put together with these logical ors. And the example here, we have 2 variables being x and y, 4 literals being not x, y, x, and y. So we're like repeating the count of y. And there are 2 clauses, the 2 parentheticals. Then we talked about CNF, like a special type of Boolean formula. Basically, it's a bunch of these clauses that are put together with these logical ands. So of these 5 examples, we said the first one was not in CNF because it has an implies, which is no good. The second one is not in CNF because it is an or of ands. The third one is in CNF because it is an and of ors. So just make sure you remember that. Fourth one is in CNF. It's just a singular clause, which is fine. And the last one is in CNF because it's two clauses put together with an and, but the clauses are just one literal each, which is perfectly okay. And then there's the question that, like, okay, the SAT solvers that exist, these pieces of code that solve SAT, they really want your formula in CNF. But not every formula is in CNF. So isn't that an issue? And we said, hey, actually, we can transform a formula to CNF through something called the Seton transformation. And we started to go through it. I decided we're not going to waste the rest of the time going through it because I don't think it's super important. If you want to see the full explanation of the Seton transformation, you can look at the lecture notes. But all you need to know is that it takes a Boolean formula, converts it into CNF, like an equivalent CNF, and then we can use that in our solvers. Okay. Questions regarding anything thus far? That was all our review of last week. Cool. Okay. So we're going to be dealing with these SAT formulas a lot, and for that we're just going to introduce a little bit more notation so as to reduce the amount of writing that there is. So like if we look at these three formulas right here, phi 1, phi 2, phi 3, they're very similar to one another. For example, this first one and second one are nearly identical, except the variable or the literals within here are just swapped around a little bit. And 2 is similar to 3, it's just that we swapped the two clauses. In essence, they kind of mean the same thing, right? Like x2 or not x3 is pretty much the same thing as not x3 or x2. Like the order doesn't really matter. And so we'll take advantage of this to basically describe SAT formulas in set notation. So I'll give you something called compact form. We're going to write this as a set. And the way we would do this is to construct an element of our set. We would look at the first clause. This is x1, so I'll put 1 here, x2, and not x3. So that is my first clause, my first element. My second clause will contribute a new element. So this would be 2, not 4, 5. So it's just a compact way of writing our CNF. And we'll do this one here. This would be 2, not 3, 1, 2, not 4, 5. So, it's a set. The order of the elements don't really matter, and the order of the elements, or the characters of an element, also don't really matter. Make sense? Questions? It's just a simpler way of writing things. So yeah, you can also convert the other way around. If you're given a set, you just put disjunctions in between the characters of your element. Cool. Okay, now for a little bit of history. Mini-SAT. This is like a very important SAT solver. And it was created by these two PhD students who happen to have the same name, but I think like 60% of Sweden has that name. Maybe not, that's just a joke. And yeah, this was like in the early 2000s. If you heard for last lecture, I mentioned like in the early 2000s, late 90s, there was this SAT revolution. So this was part of it. And yeah, it's the SAT solver. It was very small. It was only like 600 lines of C++ code. But it worked really, really well. There's this thing called the SAT competition, which sounds like the nerdiest thing in the world, and I'd agree with that. But apparently it's held yearly, so we can take a field trip there if people are interested. And it won, it didn't win. In 2005, they took home the silver medal. But like the structure and ideas behind mini-SAT are what inspired a lot of SAT solvers that are used in modern day and like everything that came after it, including PicoSat, which is going to be the solver of choice that we use. So yeah, PicoSat, it's a pretty simple to use. It's open source. It was created by this dude, Armin Beer. He's actually one of the leading researchers in SAT. He published a lot of books and papers, including the Handbook of Satisfiability. of course, had to compete in the SAT competition. 2007, won, took home the gold medal. And yeah, it was written in C, but it has bindings to Python and other languages, which makes it great for our purposes because we're going to be using Python.
What exactly are bindings?
It's just like a conversion from like one language to another. Like if it's written in C, we would run it in C, but like, oh, let's just convert it to Python so we can run it there. Okay. Yeah, so let's actually use picosat. So we have this formula here, which is in compact form, but I've also, written it there in long form. And let's see. Okay. You don't necessarily have to follow along because it's very short, but let's see. Is this like reasonably visible? Yeah? Okay. So first you would like import what's called picosat because it's Python. So you can do that like with pip install picosat or pip3, just depending on how your environment is set up. For me, it's already done. And then you would import picosat. And like to actually solve it, it's very, very easy. So first you would like describe your CNF formula. And this is going to be a list of lists. So we'll fill in these inner lists. And within each of these inner lists, you would write what variables construct your clause. So for example, here, x5 is my first clause. So I would just put 5. That's the first clause. The second one is not x4, x1. So to denote negation, you can use a negative sign. So -4, 1. And then I'll just do it for the rest of these. -4, 2. 4, -1, -2, what is that, 5? 4, 3, 5, -4, 5, -3. Did I copy that down correctly? Yeah?
Yeah.
Oh, well, I mean, who cares? Okay, cool. And then to actually solve it, we'll print out picosat.solve CNF. And then when I run this, okay, that's not good. That's
I
unfortunate.
think sometimes you have to hit like Control S on VS Code for it.
Mine's autosaved.
Here in data.
Okay, let's just do it this way. Well, this is
You're
unfortunate.
on data directory.
Oh, am I? Okay. That helps, yeah. Okay, cool. Thank you. So yeah, when we run it, we get this is output. 1, 2, -3, 4, 5. That basically corresponds to, we'll set x1 to true, x2 to true, x3 to false, x4 to true, and x5 to true. Pretty simple. One thing to note is that picosat is deterministic. I might say picosat, I mean picosat, same thing. It's deterministic, so it's always going to give the same assignment. So like if I run this over and over again, it's always giving me the same thing. But like if we actually think about it, if we have a formula that has one satisfying assignment, and think like we might have hundreds of variables, it's probably likely we have more than one assignment, right? Like it's probably, one assignment seems kind of unlikely. So if I see this assignment, how can I change my formula to get a different assignment as output?
Like rearrange the way that it's not technically changing the essence of the formula, but rearrange the order, like how you have 5 1, 5 2, 5 3 that are logically the same thing. But just rearrange that.
Okay, maybe. Let's see if that works. I've actually never tried this. So let's do something like that. We get the same thing. And let's try one more. Still getting the same thing. So rearrangement doesn't work. Is there something that we can logically change about the formula to get a different output? This is a tricky question. That's almost a hand. I'll take it.
This might be dumb, like changing the order of 1, 2, 3, 4, 5.
Oh, like the different variables?
Yeah.
Like, okay, instead of x5, let's call that x1.
Create a mapping.
Yeah, that could work. Yeah, but then I think like we would still get like the original x3 would still be false.
But the output would be different.
Output would look different. That is actually a technically correct answer. Another idea?
Maybe it just gives you it just tells you that there's no output, but you could try like adding a 6, like one more, basically a clause to that.
Mhm.
That's just, for example, -1, which is forcing 1 to be false, and then if there's any output with 1 being false, you'd know that.
Yeah, great idea. And in fact, we'll just take that and broaden it a little bit. We're just going to add a clause to this that says, and not x1 or not x2 or x3 or not x4 or not x5. So what this is saying is that like once I feed this new formula into my SAT solver, if there does exist a solution, that means every clause must have evaluated to true. So my original formula will still evaluate to true, but critically, this part must also evaluate to true for me to get a new output. And if we were to test our original output on this clause right here, that would evaluate to false. But a new output would make this true because we're just flipping every variable. So like, if we're actually demoing this and we see it, like there we get a different output. So just a bit of like logical exercise. Questions? Okay, cool. Let me just check how I'm doing. That seems like pretty annoying to do though, right? Like if we want to see a new output and we just keep on adding these clauses, that seems like it would be pretty annoying. Luckily, we don't have to do that, and we will show a different method of doing this. So there's this method called itersolve, which will return like an iterator, and we can just basically go through all of the different solutions. So let's just create a for loop. So for assignment in picosat.itersolve CNF, we will print the assignment. And now when we run it, we can see like a bunch of different outputs. Yeah.
So in the background, it's basically doing the same thing, right?
Yeah, actually, that's pretty much what it's doing. It's finding a solution and then adding that extra clause as a constraint. Yeah. Make sense? Yeah, these are like the only two methods that really matter, solve and itersolve. In fact, I don't even know if there are other solvers. Yeah.
Are we going to go into like the actual algorithm that this uses to do a lot better than like brute force?
Mm-hmm. Okay. That's fine. Let's go back to here. Yeah, so it's like 2 lines of code, right? Not that bad. What's the big deal? Like, why am I spending so much time on SAT? Like, why is this such an important question that's taking up so much time? And the main reason for it is just because of its easy to understand structure. We know that there are these clauses put together by ands, and within the clauses we have another structure, literals put together with ors. It's pretty simple to understand, and the structure is like really, really nice. It's not changing too much. And because of that, like, it makes it the go-to for showing equivalencies. So maybe you've heard of reductions. If not, that's completely fine. All you need to know is that reductions are a way of showing 2 problems are equivalent. So we would take one problem, reduce it to another problem by basically describing it as an instance of another problem, and then we would say, these 2 problems are equivalent. So it turns out that a lot of problems we can represent as a SAT instance. And that's good, because then we can just use our SAT solver to solve these other problems. So we are going to take a look at some of those other problems. But before that, we just need to broaden our logical vernacular. So, here's a couple of like Boolean expressions, and the goal is to express these in CNF form, in CNF, compact notation. So some of these are harder than others. So, I'll take volunteers if you want to try it. Otherwise, I can just quickly go through them. Pick your poison. Just choose one or two, and I'll do the others. Yeah.
The implies one is just directly, I think it was the pro tip from last time.
Yeah, I showed the pro tip. Do you remember what it was?
Not X or Y?
Yeah, X implies Y is logically equivalent to not X or Y, or like in compact notation, not X, Y. That's true. Okay, if that's implies, then what is by implication? Someone else. Yeah.
That or X and not Y. Or that and X or not.
Yep, perfect. So this is equivalent to saying like X implies Y and Y implies X. And then we just use whatever we got before here. So this would be not X or Y, and then the second clause would be not Y or X. So kind of jump to compact notation, but yeah, that would work perfectly there. Any ideas for XOR, X or Y? Yeah, Thomas.
Would be X and not Y, or Y and not X.
Yeah. X. So this would be X and not Y, or Y and not X. That's what you said, Thomas? Yeah, so this is like the first step. There's like more, but that's a logical first step. From here you can apply a bunch of distribution and like simplify it down. And eventually you get something to like X or Y and not X or not Y. And like if you really take a moment to think about this, it makes sense.
Yeah.
Because XOR is like normal OR, except we don't want both of them to be equal to true, so we just exclude that condition. So yeah, that's that in CNF. What about the last one?
I think just writing this down, this is basically, I think it's logically equivalent to X implies Y and not X implies Z. And if that's correct, then it's easy to do.
Yeah, so that's correct, and then we can apply the pro tip. So, implication is pretty similar to if-then. So if X is true, then Y. So X implies Y. But also, if X is not true, then we have Z. So we just write it in terms of implications. Then use like whatever breakdown we did here on both parts, and you'd get it. So I'll just show the answers, and that's that. Good so far? Okay. What about these? So we'll start with the first one, all, meaning all of x1 through xn must be true. Let me just erase some of this stuff. Yeah, so how would we do all? Yep.
Just x1 and x2 all the way up till and xn.
Right, yeah, like if we wanted to evaluate a true, all of them have to be true, and we just check that by doing logical AND. And this is in CNF, because it's just, singular clauses. So in compact, it's x1, x2, up to xn. Okay, what about ALO, at least one? What are the variables?
Not x1 and not x2 all the way up till and not xn.
At least. Can't you use or then?
But that's not.
That is X1 or X2, it's one clause.
Oh yeah, then you just all of them. I thought that's not.
Yeah.
A lot of what you want.
Yeah, because this can evaluate to true if all of them are false.
Yeah.
right? So that wouldn't quite work, but I heard some people mention it. We could just OR all of them. Like that's the definition of what OR is. Like it evaluates to true if at least one of its arguments are true. So in compact, it's like x1, x2, like a singular clause constructed of all of those. At most one is a little bit tricky, and I'll just show you the answer because I don't want to spend too much time on it. But suppose we had the solution for at most one, then how would we solve exactly one?
I did it kind of the reverse way. Like I thought of the solution of exactly one and then got the solution of at most one.
Oh.
Exactly one is just at least one and at most one.
Yeah. Like if we had the solution
I
for...
get, but like the reason why I did that was I thought can you do exactly one without n clauses? Oh yeah, I thought you needed n clauses for exactly one. Like it's just x1 and like everything else knotted, and then x1 like not x1 and x2 and x3 onwards knotted.
Yeah.
And so on.
That's a lot of clauses though, right?
It's n clauses. Yeah.
Yeah. So like, yeah, there's a lot of different encodings you can use. So we'll just look at this at most one briefly. So here we're saying we have a bunch of clauses that are two literals within it. In this case, we're saying not xi or not xj. And the way you should think about why this is true is that like we would not have at most one if we had two or more variables being true. And if that's the case, then when we look at a pair of variables and we choose the two or more true variables, when we plug it into here, that clause would evaluate to false. And then the entire expression would evaluate to false. I wouldn't worry too much about like this encoding. It's just like nice to know. But I guess the question is like, how many clauses are in this particular encoding for at most one? And choose two, yeah. Like over all pairs, we're just making a clause. So that's like O of n squared. It's quite a lot of clauses.
I have a question.
Yeah.
So with that, like that would be O of n squared clauses, and I think the way I was suggesting it, you'd probably end up with like O of n clauses, but each clause would have n literals within it. So which one do you sort of prefer?
That's a really good question, and we'll talk about it in just a little bit. But really, it comes down to like whatever works better. There's no like universal best rule that like, oh, we must optimize clauses or we must optimize size of them. It really just comes down to let's just try and see what happens. So that brings me to the point that like, we had n choose two clauses here. There's this encoding for at most one, which is too complex for me to explain right now. It's not worth learning. But all this is to say is that like this is a valid encoding, and here we introduce new variables, log n extra variables, but the amount of clauses is now n log n instead of n squared, and these clauses are very small in size. All of this is to say that like many different ways of solving the same problem, but they have different pros and cons about them. The first one was simple, but it had n squared clauses. This one's more complex, but it has less clauses and they're small. And yeah, this is what we just talked about. Like, the performance of a SAT solver can vary hugely, like depending on the encoding, and like different encodings work better in different circumstances. So you just gotta figure it out. And the general tip is start simple, and then add complexity as needed. Okay, questions? How am I doing on time? Not very good. That's all right. Let's shift focus. From SAT, we're going to look at the graph coloring problem. So, what this problem says is we'll be presented a graph. V1, V2, V3, V4. And we're given a parameter k, in this case 3. And the question is, can I color my graph using k or less colors. And by coloring, we mean give a color to each of the vertices. So maybe like this one I'll set to red, this one I'll set to blue, this one I'll set to blue, and maybe this one is green. So I give colors to each of my vertices, but also when I look at any edge, its endpoints must be of different colors. So in this case, this is a valid coloring. But if this was, say, green, that would no longer be valid because this edge has green endpoints. Okay, so that's the graph coloring problem. As it's stated, is this question a decision problem or an optimization problem? And just to refresh the memory, a decision problem is a problem where you simply say, yes, there exists a solution, no, there does not exist a solution. Optimization is, let's find the best possible solution. So as I've stated it, which one is it? You got a 50-50 chance if you just guess.
Decision.
Decision? Does anyone disagree? Okay, good. Yeah, it's a decision problem. Okay. Hopefully we can see all of that. Okay, so what we're going to do is take this graph coloring problem and we're going to convert it into SAT. And the reason why we want to do it is like if we can convert this graph problem into an instance of SAT, we'll just feed that into our SAT solver and we would have solved our graph problem. So we don't have to even solve a brand new question. Naturally, how do you get from graph to variables and logical notation? So really, there's like a couple of things we need to keep in mind. We have to define our variables somehow. And then we have to encode constraints. So just to visualize what we're doing here, we're going to take a graph, we're going to construct this arrow, we're going to construct a way of transforming it into phi, such that if our graph problem has a solution, then so does this SAT instance that we'll create. And if this graph problem does not have a solution, then neither does our SAT thing. And like an important thing to keep in mind, because like a lot of this is very abstract right now. Like, I still don't understand how graph relates to logical variables. One thing to keep in mind is that suppose we had this formula given to us, like the encoding already given to us, then in an ideal world, we could look at the solution for this SAT formula, like what the variables are assigned to, and that should pretty much immediately give us what the coloring for the graph is. Or conversely, if we had the graph and we had its coloring, we should pretty much immediately tell what the variables should be set equal to. Yeah?
Is the encoding that we are doing to this SAT problem supposed to just answer the decision problem, or is it also supposed to give us the assignment? Like, should we relate like the true-false assignment of the variables to the colors as well somehow, or is the assignment just supposed to tell us that, okay, this graph can be colored in less than equal to k colors?
Yeah, like, I mean, since it's just a decision problem, it'll just be like yes, no. But how we encode things, like if it, like our SAT solver, it gave us what the assignment was, which we didn't need that. We just needed to say yes or no. So like if we were to get that assignment, ideally that would also give us the coloring if we're smart about our encoding.
So we're leveraging the assignment to get the colors as well.
Yes. Okay. I understand this is kind of abstract. So I will sort of just get us started and then we'll go from there. So, suppose we have these vertices v1 through vn, and we have a bunch of colors, c1 through ck, k colors. I'm going to go ahead and define a bunch of these variables of the structure x, vertex, color. And this will exist for every single pair. So there will be xv1c1, xv1c2, xv1ck, like a bunch of these, nk total variables. And I'm going to have it such that this variable will be equal to true. Like in my assignment, if this variable is equal to true, then that will tell me that I want vertex vi to be colored using cj. Seems a little bit arbitrary why we're introducing this, but it gives us a little bit of structure, something to work with. Let's just say this is our variables. Now, we have to take the graph problem and make it into our formula. In other words, we have to think of the constraints that are described in this graph problem and somehow encode that into Boolean language. So what are some constraints that were given in the graph problem? It could be as simple as possible. Some things you might not even think about. Yeah.
If vi and vj have an edge between them, then their assignment with a particular cj should not both be true.
Yep. True. That's the definition of a coloring. We want endpoints to be different colors. What other constraints?
I think the most basic one is that any vertex can only have one color assigned to it. So if one of them is true, you can add it with everything else being
Every vertex has one color. We need that to be true. Anything else? I'll give you a hint. No, not really. So let's deal with the first constraint. And you'll notice that I'm saying every vertex has at least one color, not exactly one color. Why am I saying at least one color? Sure.
Oh, because the number of colors that we are assuming right now is k, but what I'm thinking is that if the actual optimal solution uses less than k, then there are, for any vertex you could shift its color to any of the unused colors, and even that would be a valid answer. So it could have 2 or 3 colors if the second or third color that we're choosing is unused. So I don't know how to explain it.
Yeah. I think
It's not necessarily unused. It can also just be a color that fits in that case, even if it's used somewhere else.
If you're assuming that we come to the smallest solution, after that would be some unused color. Because you're taking ck colors anyway. What if it's k minus 1, k minus 2 color? Then whatever color we're not using, that could be assigned to any isolated vertex or something. So.
Yeah, so this is saying if our solution says that every vertex has at least one color, then maybe it'll output that vertex v3 is green, red. So there are 2 reasons why I'm saying at least one color. The first reason is that if there is a solution where a vertex can be red or it can be green, great, I'll just ignore the other colors. I'll just choose one of those colors because all of them work. The second reason is because if we said exactly one color, we would have to use the encoding for exactly one, which we just talked about, which uses at most one, and we said that's a little bit annoying, that's too much effort. At least one was a very simple encoding, so it would be okay. Do you have a question?
Yeah.
Yeah.
With the previous set problems, it was easy to have the negation of some literal, because there are only 2 states.
Mm-hmm.
But in this case, we have k states. So what happens when some literal is negated?
So these are our variables. That will still only have 2 states. Either this is evaluated to true or it's not. It's just that we have a lot of variables. So before we were calling the variables x1, x2. Now I'm just describing them a little bit with more information. It's xv1, c2. This is a singular variable that is either true meaning vertex 1 has color 2, or it's false. Okay, other questions? Okay, then how do we encode at least one color in terms of these variables? I mean, I'll just give it to you because it's just what we saw before. It's like that disjunction. You know, we'll take a vertex, say VI, and VI must either be colored color 1 or color 2 or all the way up to K. So one of these must be true. It's that disjunction. And we do that for every vertex. That's the first part. Now we'll turn to the second part. Let me just check how much time I want to spend on this. Okay, let's just build the intuition for this. I won't spend too much time on it. As it's phrased right now, like, we're dealing with like a lot of edges and a lot of colors, so let me simplify it to just one thing. So So what I've written on the board is like, if VI is colored C1, then VJ is not colored C1. And what this is saying, like, it's very simplified form. Ideally, we'll go over every single edge. And we'll say, if this vertex is colored some color, then the other vertex is not colored that color. And we would go through that for every single edge. So this is like a single instance of it. We're looking at the edge VI, VJ, and we're considering the color 1. If VI is colored C1, then VJ can't be colored C1. This is like a constraint we would have to check. So how do we encode this?
Yeah, so what I thought of was just building off of that, because you can convert the implication to the OR.
Mm-hmm.
So
like, what's the implication?
So it's basically not of X V for all colors basically. Or okay, we have to look
Just for this.
Not of X V I.
Before that.
Sorry.
Before that, like the step you do before that. You're taking the implication and breaking it.
Yeah. So you're saying not for the first one or the second one, right?
X, V, and C, J implies.
Yeah.
Not VI is not colored C1 or VJ is not colored C1.
Yeah. So, like, if we translate words to logic, if then is an implication. This first part, VI is colored C1, is equivalent to what this variable is, X VI C1. And if that is true, then VJ cannot be colored C1. So this variable, the opposite of that. We can't have VJ colored C1. And then we can use the trick and break it apart. And when we do that, we do this over all edges and all colors. And it looks something like this. I will pause for questions here because you might want to remember this. What this is saying is that for every edge and over every color, if one endpoint has that color, then the other one endpoint cannot have that color. And then we just break it apart, the implication. Yeah?
Why did you not write it that way? You wrote it the opposite direction, where it's if there's two. Oh, never mind. Sorry, let's write.
Yeah.
This looks suspiciously like the at most one thing that we did earlier,
Mm-hmm.
taking them two at a time and then not.
Yep.
the edge of the thing.
Yeah, just
Is that coincidence or?
well.
I think like you can read that as at most one color on an edge, like at most one.
Yeah,
color.
for color C, at most one of those variables can be color
Oh,
C.
so you would have straight come to that if you thought of it that way.
Yep, that works. Okay, let's solve this problem. I'll post all of this so you don't have to like copy this. So what I have here is a graph with 120 vertices and like too many edges for us to count, 1,276. We're gonna solve the question. So like a lot of boilerplate code is here. What this is doing is just saying like, okay, if I have the variable as I've written here, let's convert it to a number, because when we did this here, we represented our variables as singular numbers. So like that's what that is. Here, it's just going to tell us how much time things took. So let's implement some of the constraints. So the first constraint we said was every vertex gets a color. So we'll just go through every vertex. Don't worry about how the for loop is set up. It's just like the numbers had to make sense. So it's just starting from 1 and going up till n. And what we're doing is like we're adding a new clause for each of these things. And let me just write it first and then we'll talk about it. So the first constraint, remember, we looked at the variable and we said, or the vertex, and we said either it's colored C1, or it's colored C2, or it's colored C3, all the way up to CK for a single vertex. That's exactly what we're doing here. We're creating this clause, which is that variable xvc, so the vertex v has color C, and we're iterating over all colors. So that part creates the clause, and then we're adding it to our formula. Make sense? Kinda? Not really? Kinda? Maybe? I don't know. Okay, that's the first constraint. The second constraint was if uv is an edge, then u and v have different colors. And I'll code this first, and then we'll talk about it. So first, like we said, we'll go through every edge, then we'll go through every color, and then we'll say if endpoint has this color, then other endpoint can't have this color. So for C in range colors, we will append that like at most thing that we just talked about. That's what we just saw before. This is saying, if we put this back in implication mode, it's saying U is colored with C implies V is not colored with C. Make sense? Questions? Okay.
I have a very basic question.
Yeah.
How does the if you go down,
Yeah.
how does the V in range, 1 to n plus 1,
Mhm.
in general, like, if I did 10 to, for example, is that second number like where you should end, or is it how many numbers you're counting?
You go up to this number,
And don't include it.
but not include it.
So if you did 10, n plus 1, it would be 10, 11, 12, all the way up to n.
Correct,
Okay.
including n. Yes. Okay, so this graph can be colored using 9 colors. We're going to test it with 10 colors. And like this is just solving the CNF. So let's see what happens. Okay, we get an assignment which, has a bunch of variables, but like the key thing to note here is that didn't take that much time, right? That's pretty good. And like if we try 11 colors, should this take more time or less time? Well, like left hand up if you think more, right hand up if you think less.
Wait, which hand is what?
Left
Right.
is more, right is less. Does anyone want to argue why they think one way or another?
You're increasing the number of clauses
Mm-hmm.
by a lot, and I get that there will be a lot more solutions, so it's easier to find one, but I'm still leaning on the more side.
I'm expecting that the number of solutions will grow more than the number of assignments.
Well, let's see. I actually don't know what's going to happen. That was more, right? Yeah, I think it's one of those things where it's like there's a lot more combinations of things to try, and it might take a little bit longer. 20?
Yeah.
A little bit more. So it seems to be a general trend. And we can try less. Here we just say unset. And look at how this took a substantially longer time, 0.27.
What about 9?
9?
Oops, even that is increasing, like 7, 8,
9 was pretty quick.
9 is lower than that.
Yeah.
Let's see another example really quickly. It's just a different graph, but I'm just going to copy these constraints over.
Could this more or less thing also depend on like the language used? Like, could it be faster in C? Like, could the trend be the other way around?
It could, but likely not. Okay, so this has chromatic number 6, so it should color with 7. It does, very quick. If we try 6, also quite quick. If we try 4, also quite quick. If we try 5, this is going to take about 10 minutes. So I'm not going to let it run.
Have you?
Yeah. Yeah, let's keep that in mind. It takes about 10 minutes, and we'll come back to that. Because that's an issue, right? Like if we chose to look at this and test 5 colors, we don't want to sit around waiting for 10 minutes. And we'll figure out how do we handle that.
Is there a solution or no?
For 5?
Yeah.
No. The chromatic number was 6. So no more than 5 or 6.
Why does it take over?
We will talk about that in just a little bit. But you can start thinking about why it takes so long. Okay. When I posed the question, we said it was a decision problem. Yes or no, there is a coloring or there's not a coloring. Suppose we wanted to look at the min coloring problem, which is the exact same problem, except now I just give you the graph and I ask, what's the least amount of colors we need to solve it? How do you solve that? And hint, you can use the solution we just came up with. Yeah.
Just start from 1 and keep running the algorithm until you get.
Yeah, all right, try k equals 1. If that doesn't work, try k equals 2, so on and so forth. What's the runtime? Log? Long. True? Yeah.
Are you given an upper bound, like for example, like k equals 80 is possible to color it? Because I think it would be a lot quicker to go there and work down rather than start.
Or so binary search.
No, not binary search. Just do like, I'm saying 80, 79.
No bound.
It would be a lot quicker.
No bound. But I mean, if you had the graph, you could have a bound as like the number of vertices, because you can't color.
I still
Like,
think that also might be quicker.
yeah, it's going to take a linear time in terms of like the min coloring, like the chromatic
I think
number.
going from number of vertices down would be quicker than.
You can actually use like a binary search approach where you like jump up by a power of 2. It's a little less intuitive to come up with. So you basically try 1, 2, 4, 8, 16 until it doesn't work, and then you binary search within that range. That takes log of the chromatic number time. Better, but not great. So that's just like another problem you could solve. Here's a different problem called unset. And this is like, given a graph, and now this integer k, is it such that no matter how we color the graph using k colors, it is not possible to color it? Is this problem harder or easier than our graph coloring problem? Yeah. Equally hard. Why?
Both are NP-complete.
That's a true question. Maybe I didn't pose my question correctly. Which would take longer for us to solve?
Based on what you said about the 5 thing, I'm guessing unset.
Yeah, right. When we tested 5, we knew it wasn't going to color it because the chromatic number is 6. We were told that. That took a really long time. But why? Like, what let's actually get to the question. Why does it take so long? Yeah.
I think because if you want to show that there's no valid K coloring, you have to test every K coloring, whereas if you want to show that there is one, you just have to find it.
Perfect. Yeah. With unsat, we have to test every single coloring. When we're checking graph coloring, if we get a coloring, we stop. No more searching. So it's much less time. Yeah.
But for 4, it did still like complete quite fast,
Mhm.
but it was answered.
Yes. But like, since we had less colors to use, there were less combinations we had to check through. Question? How am I doing on time? 20 minutes? Okay, I can work with that. Yeah.
But when we were doing the pi sat thing or whatever, pi sat thing,
Mhm.
like wasn't like we discussed like one way to see all the possible solutions or whatever by like adding those clauses.
Mhm.
Does that also go through every possible iteration or no? Like
I think if it's
Like-
doing it as an appending thing, the only problem is in the last run of that, I'm assuming it runs it once, gets the unsat as its output, and then it gives you an output.
So like itersolve would like give you an iterator that you could go through. So I guess in that sense, it is checking all the satisfying assignments.
so is that as hard as unsat?
The last run has to be, right? Because after you appended all of the
Yeah,
solvable
but it-
I think it would
Unsat
take
and
the same
unsat,
amount of
right?
time. I think so, because you're still checking every search space. That's a good question. Okay, there's another reason why unsat takes so much longer and why it took 5 so much longer than 4. It's not just because there's so many combinations. I mean, here's a graph that shows time. I'm not going to spend too much time on it. The thing is that, like, there's a property of graph coloring that we as humans take for granted that our SAT solver doesn't yet know about. Because in the eyes of the SAT solver, I'm just dealing with a Boolean formula. Right? I'm just dealing with variables and stuff. I don't know anything about a graph. Like, to us, we know it's a graph because we encoded it as such. And even though we've incorporated some of the constraints, there are some extra facts about graphs that we know that our SAT solver would not know. So for example, let me just change this slightly. Like here we see 2 separate colorings of the graph. In our eyes, these are more or less the same coloring, right? Like if we look at the colors that are the same, these 2 are green. Here, these 2 are blue. That's red, that's green, this is blue, this is red. All we did was sort of like shuffled around the names of the colors, right? Like to us, pretty much the same thing. Agree? Yeah. However, in the eyes of our SAT solver, they're not the same. For example, if I look at this 4th vertex, v4, in this coloring, our SAT solver would say that the variable x v4 comma blue is equal to true. But here, it would not say it's true because the thing is not colored blue. Because of that, it's going through all of these colorings that in our eyes are basically the same thing, but it's going through these, it's computing those. And that wastes a lot of time because we can really reshuffle these color names however we want. And it's just checking the same thing over and over again. So for example here, like these 2 graphs are essentially colored in the same way, right? The left 2 are one color and the right thingy is a different color, or like 0 and 2 are the same color, and 1 is a different color. To our eyes, we know that those are the same. To our SAT solver, it doesn't know that. How do we fix this problem? And yeah, like when I first heard this question, like how do you fix this? I was like, I have no bloody clue. Like this seems like a really, really hard thing to fix. So any guesses are okay.
Like in this example, it just seems like somewhat like a negation, like the symmetry thing, like the complement of thing on the left is the right.
Yeah, but I mean, that's probably because there's just 2 colors. If you have like 100 colors, then it's just like rearranging the colors. Anything?
Like if we get like we run it and the moment we get like a valid coloring, after that can we try running it with just instead of all of them from C1 to CK, just those particular.
But we don't want to run it to get the coloring because we're solving like this unsat thing, which takes a really, really long time, right? It's going to go through this search space. So how can we prevent it from, how can we say, yes, you can check this one, but I don't want you to check that one?
If 2 of them are symmetric, can we think about their superposition? Like if
Too complicated. Yeah.
If we assign sort of say your vertices are numbered and even your colors are numbered in a way, can you basically say that the first vertex has to get the first color?
Yes.
Then the second vertex, all of its edges, you give them a second, and you work it that way. Always use the lowest available.
Yeah. Or basically the idea is at the start, I'm just going to say, I want vertex 1 to be blue. And I want vertex 2 to be red. The other vertices you can explore on your own, but let me just fix these vertices with these colors. And if we fix those and encode that into our SAT, then we'll never explore all of these duplicate things because we're saying this variable has to be this color. So I'll show it in code and explain it as we go. So we're doing something called symmetric breaking. So what I'm going to do is basically append a new clause which says variable 1 vertex 1, you're going to be the 0th color. And maybe some other one, variable 2, vertex 2, you're going to be color 1. It's saying 2 vertices, you are these colors.
You know that there's an edge between 1 and 2?
No. Is it at 5?
How can you do both of those parallelly if you know that there's why can't they just be the same color?
They could.
No, but isn't that removing some solutions?
No, because I remember the encoding was at each vertex has at least 1 color.
No, I agree. I'm saying if you're isn't it possible to construct a graph
Mm-hmm.
where if you fix the colors of 2 vertices to be different,
Mm-hmm.
then it's not k colorable, it becomes k plus 1 colorable, for example.
Maybe. So
If you
admittedly, this solution, you might have to do some trial and error. This we may have gotten lucky because it's such a big graph. So perhaps there are some edge cases, but this is the main thing that to prevent it from searching everything, let us just fix some certain things. So yeah, we could have looked in the graph and said, okay, these 2 are connected by an edge. Let me just fix that. But for the sake of example, I left it as that. Okay. Let's just run through the rest of this. Yeah, so the idea is that we started out simple, we encoded our constraints, but we needed to add just a little bit more complexity, just add a little bit more constraints, and that greatly reduced the amount of time it took to run. So there is this nice balance that you have to find about keeping things simple, but also adding constraints. So some constraints may seem unnecessary, but they may help in reducing the overall time. Thomas?
Do we necessarily need to fix 2 colored vertices?
No, I could have picked 3 if I wanted to. It was just 2 for the sake of example.
So 1 works as well.
One might not reduce.
One might not. Let's just try it. This is a pretty easy thing to do.
I think it might take a minute or 2.
Yeah, this is going to take a little bit longer. So it's reducing it by a little bit because we're saying that, yeah, there you go. It took 7 seconds. Not that bad, so 1 works.
Is there a maximum number of colors you have to fix?
Do as many as you want before it breaks. It's best to keep it simple because otherwise you're just adding so many constraints. And since most cases you don't really know what the graph looks like or the graph is too complex, then it's just a bunch of trial and
Why
error.
would it break? Wouldn't it just give the wrong answer? If you fix every single color, it would say
Yeah, it would give a wrong answer, so to speak.
but any arbitrary 2 will guarantee the right answer.
If you have a square and you fix opposite ones, that doesn't work, right?
Yeah.
Yeah,
If
because
you fix them to be different,
I
it'll
thought
give
they
you two to be unsolvable.
have to be
unsolvable.
But
on
it
the
is,
same
yeah.
edge.
Yeah. Okay. Yeah. So like we said, this is a not foolproof solution. However, like, if we're testing it on these smaller graphs, we would ideally like do this symmetry breaking a couple of different times, not just one time with like these two colors. We would say like, all right, let's try it a different time with this variable and this color. Keep on doing that until you get a solution. The point is like a very easy way to reduce this runtime is just by like fixing certain things, adding constraints. Yeah.
I have a question.
Mm-hmm.
Why doesn't it just take 25 times the amount of time it took us to run it when you fix 2? Because you're just like, you have 5 options for the color of the first vertex, 5 options for the color of the second vertex. So even if it's brute forcing its way through that, like it took like 0.4 seconds. Why doesn't it just take 25 times that?
It's probably stuff that's going on under the hood where it's not necessarily like a linear thing. Maybe there's some sort of like parallel processing going on like behind the scenes. So I don't really know how like the inner workings of it to like a T, but yeah. Okay. Just did that. Let's see. Like 10 minutes. Okay, we're just going to breeze through this very quickly. I won't spend too much time. But this is just another problem that we could encode into SAT, which is the stable matching problem. You have n men, n women. Each man creates a preference list of the women, their own individual preference ranking. The women do the same thing for the men. Each woman creates a preference ranking of the men. We want to create these one-to-one matchings where basically everyone is happy. There's no blocking pair. And like we can encode this in SAT. And like, here's an example here. We've defined these variables, which actually, let's not even go through this. It's kind of going to take too much time. But okay, let's take a leap of faith here. I have successfully encoded stable matching into SAT, and I will solve it using my SAT solver. Hooray. But why would I do that when Gale-Shapley exists? Do people kind of remember Gale-Shapley? Yeah, it was this algorithm that literally solved the stable matching problem in linear time. And we're going through this complexity of taking stable matching, transforming it into SAT, and then shoving it into a SAT solver. Why would I ever choose to do that when Gale-Shapley exists?
Is this encoding the exact same as the original Gale-Shapley problem, like no ties and like?
Yeah. The reason is that once you consider mutations of the Gale-Shapley problem, Gale-Shapley no longer works.
Yeah.
That algorithm works only for the stable matching problem. So there are these other problems like SMTI, which says like your preference list might be incomplete or there might be ties. That's a reasonable thing to like expect to happen. Like if there's n men and n women, I might say, woman 3 and 4 are like the same in my eyes. I don't know. But like, we can see examples of this in the real world where that could happen. Gale-Shapley no longer works. Or SMC. This is stable matching problem with couples. And the idea of this problem is like, you can imagine a husband and wife or like some sort of couple who are applying for residency programs. They're applying for like hospitals to work at. And, okay. If they were to rank their residency programs individually, like I might choose, like Penn, NYU, Harvard, and then my wife might individually say, like, oh no, I want to go to Miami instead first. But together, if we were to work together, we might say our ideal pairing of residency is like me at NYU, you at Penn, because they're like geographically close together. That's like the idea of this problem. So indeed, like Gale-Shapley can't handle that when we're matching couples to, pairs of outputs. All of this stuff could be encoded into SAT just by like adding a couple more constraints. So all this is to say is that like, sure, some problems might already have solutions that exist for it, but once we consider mutations of the problems, slight deviations, they may become NP complete. And we still would want to solve those problems. so we can turn to this SAT. Let me just finish up and then we'll. Okay, so that's pretty much the content for this week. Yeah, I think this last part that we sped through about stable matching, not super important. It's just important to know that we can take these problems, convert them into SAT. So yeah, next week we're going to start learning how the SAT solvers work. So I know some of you were curious about that. We'll start discussing that. Homework 1, you'll be working with encoding problems into SAT. I believe it's like a Sudoku puzzle. So you'll learn how to convert that into SAT and then solve that. It'll be due in 2 weeks. I will likely release it tomorrow sometime and then give you 2 weeks plus maybe a day or I don't know. I don't know. I'll just give you at least 2 weeks to solve it. No less than 2 weeks. Yep. And then as always, stay healthy. Here's a nice quote. If you want, you can read it. And then if you want, additional reading is up there. I'll try to post the slides and the notes tonight, though I get home pretty late, so we'll see about that. And I've also attempted to record this lecture, so you can also view that if needed. However, this is not a substitute for attending lecture, because attendance is part of your grade. Cool. Okay, you guys are free to go, and I'll see you next week.